The next talk is from another colleague of mine from European XFEL. It's Thomas Kluyver, who's also a well-known figure in the Python community, so I understand. And he's going to talk about down to the bytes. Can we simplify alternative access to HDF5?
Great, thank you. Yeah, good morning, everyone. I'm going to try to keep myself standing here because I know over there is not quite visible on the webcam, but I may start walking around during the talk. So yeah, what do I do? I work on the H5Py Python library, which is one of two main Python wrappers for HDF5. The other one is PyTables, which Francesc, who spoke yesterday, works on. H5Py kind of tries to stay closer to the HDF5 data model, I think. PyTables more uses HDF5 to implement its own model. So I imagine many of you have seen this sort of thing already, but if you haven't used HDF5 from Python or a high-level language, then it looks something like this, where opening a file, we're looking up the data set by path, and then we're slicing out the part of it that we want. So this is kind of the Python syntax for like hyperslab selection. I also make work on H5 Glance, which is primarily a terminal viewer, but also has a Jupyter Notebook component for HDF5 files, because I spend a lot of time SSH'd into a server where starting up a GUI program is just kind of enough of an extra hassle that I want to be able to look at things in a terminal. And it kind of works particularly nicely for deeply nested HDF5 structures of groups, because that's something that we use at European XFEL quite a lot. And then within the context of European XFEL, I work on a package called Extra Data, which is kind of a higher level abstraction built on top of H5Py to get to European XFEL data, hiding a lot of the details of like the file format and multiple files and things like that. I'll talk a bit more about that in a moment. Yeah, so this is kind of the background of where I'm coming from. And this talk is possibly going to seem like a bit of a random collection of bits and pieces, but I hope that this is kind of the idea that ties it all together. The HDF5 file format is super versatile, as we all know. There's all of these possibilities for like different data storage formats, chunking it in different ways, filter pipelines, different types of external data, custom data types. Like there's a million and one things, and there's more new things coming, like Onion VFDs and Swimmer and things like this. And for any given use case, I mean, like European XFEL, we're only using a tiny fraction of these possibilities. And I imagine that there's a lot of people in kind of a similar boat that, you know, you have a whole system built around HDF5, but you're really building around just like one particular corner of HDF5. And of course, it's not the same corner for all of us. Like we can't just throw away 80% of HDF5. Like different people use different things. Like we have so far like not used Swimmer at all. Like it's just not useful in our cases particularly. But there are other people using that. So yeah, we have all of these different cases that are kind of only touching maybe like 10%, 20%, 30% of the features of HDF5. And re-implementing HDF5 completely is an enormous task. Like it's a very big, complicated file format with all of these different possibilities. But implementing the subset of things that you're interested in maybe is more tractable. And yeah, so this is kind of what I think is the central message of this talk is I think we can and we probably should be implementing like more specific HDF5 reader and writer components for our particular use cases rather than everything going through one Z library that can do all of the possibilities. And just like, I don't know how many of you have looked at the HDF5 format document, But I have spent quite a while looking at it, and just to give you an idea of what I mean by complexity, like there's 4 versions of the superblock, which is the header at the start of an HDF5 file. There's 24 header message types. Many of those have their own versions. There's 2 completely different B-tree formats, 5 kinds of chunk index, 4 at least ways that I could find to refer to data in a different file. Most of the lengths and offsets specified in the file can be 2 bytes, 4 bytes, or 8 bytes, depending on something set in the header. So just to like an extra complication for every bit of parsing that you want to do. All of the versioned bits of this can be like independent. So like you can have the newest version of the superblock and then the oldest version of one of the message headers, and it's still, at least as far as I know, considered a valid HDF5 file. Some of the bits are like have padding to align fields to like 4-byte intervals. Some of them don't. So yeah, it's a complicated spec. Despite that, there are like a number of projects that have fairly heroically re-implemented HDF5, or at least substantial parts of HDF5. These are the ones that I was able to find at a fairly quick search. This is probably not an exhaustive list, but there have been at least 2 re-implementations in Python, one in Java that I think Igor is going to talk probably a bit more about later today. Yeah, C++, C#. For a lot of these, the motivation is just that within a given ecosystem, particularly for managed languages, it's often easier to install a native package. Like, if we have a native Python or a native Java package or whatever, it's kind of automatically cross-platform, cross-architecture without any like special measures, any like complicated build steps or anything. So that's a big motivating factor. And of course, if you're working in a language that's memory safe by default, then the attraction of having your HDF5 library be memory safe is also important. But this table that I found in the README of one of the 2 things called H5Coro, they're both part of the same project. It's not a coincidental name. Kind of indicates what I mean by the challenge of this. Like, clearly they have implemented enough of the HDF5 spec to do what they need to for their use case, but there's substantial bits that aren't implemented. So, B-trees version 1 are implemented, B-trees version 2 are missing. So this makes it kind of like, it's a challenge to generalize because like, I look at this and even as like kind of one of the facility experts on HDF5, I don't know what version of B-trees are in like all of our files going back for the last few years. So it's not immediately obvious to me whether we can use this library or not. So why would we want to do specialized implementations? So one that we've, one motivation that we've heard about several times, and I'm going to talk about a bit more in a minute, is parallelizing decompression. Particularly at our kind of facilities where we have HPC clusters with machines with like 40 cores or 64 cores or whatever, using just one core to do all of the decompression work for chunks is very unnecessarily slow. It's very easy to speed things up by parallelizing that. There's things about parsing other file sources. So Python has this nice kind of library/framework now called fsspec, where you can kind of use anything that has kind of the shape of a file system. So it can be an actual file system, but it can be the contents of a zip file. It can be a file on files on S3 or in GitHub, or like anything you can think of that you can kind of present as files. You can kind of wrap through fsspec, and it has a common interface to read and write that in Python. yeah, we have these performance cliffs where sometimes if you just like tweak how you're reading an HDF5 file slightly, then you fall kind of off a hot code path and onto a slow code path where it's iterating over, every number or something, and it becomes dramatically slower. And it's not always easy to understand what's going on with that because you're just relying on this big library. And there's a lot of other possibilities. My point here is not that libhdf5, the C library, couldn't do any of these things. Like, many of these things are coming, like parallel decompression, I think, as Elena is going to talk about multi-threading in HDF5 later on today. We saw things about, the new VFD swimmer looks very nice. My point really is that having one implementation that all of this has to go through is a massive bottleneck. Like all the rest of us who are not like working on HDF5 itself kind of just have to wait for things to turn up. And in principle, we could contribute ourselves, but that's not always easy. And the bottleneck kind of only grows over time because all of these features have to fit together. The people who want multi-threading, like sooner or later, someone will also want that with Onion VFD. So these things have to work together, and there's more and more pieces to it that all have to connect up and work together. So changing tack a bit to go back to sort of concrete things that I've actually worked on, and this will come back together, I hope. So Extradata is our Python library that I mentioned for data access at European XFEL. It's an extra kind of layer of abstraction on top of using H5Py. So we're giving people access to HDF5 files on a file system directly. It's not going through HDS or HSDS or something. But yeah, we're building an extra layer of support for that. And kind of the starting point is that when we take a run, so that's kind of the unit of experimental data, that's a whole lot of HDF5 files that are sitting in a folder. And then for the detector data in that, we also create another folder because the raw detector data gets calibrated. So there's another set of HDF5 files in a separate folder for the calibrated data. And so kind of the starting point of Extradata is to provide we present this run as one object. You don't have to know about all of these, dozens up to hundreds, up to sometimes thousands of files that make up the run, and it can track down like the data that you want within the right files. We also have a system of indexes, so it has stuff to align the data. It has methods to help you like break the data up into pieces, either for parallel processing or to limit memory use, even if you're just doing it one piece at a time. Because obviously, if you've got a run that's an hour long with 1 megapixel detector data coming at 5,000 frames a second, then you can't load all of it into memory in one go, even on cluster nodes with a lot of RAM. And it's all based around, we bring data into standard Python data analysis libraries. So we bring data into NumPy, Xarray, Pandas, Dask, depending on what the user wants and what sort of makes sense for that data. So this is kind of what it looks like at the bottom. You open a run by the proposal and run number, and then kind of, the very simplest thing is we're looking up some data by an alias that's defined somewhere and loading it as a NumPy array. So that's kind of the background on like Extradata, and now bringing it into what I'm talking about. So we worked on doing parallel decompression within Extradata. So some bits of our calibrated detector data get compressed in a very simple old-fashioned way, so byte shuffle and gzip. There's bits of the data that just compress super well, even without any fancy algorithms. So this was what we went for. And decompressing in parallel, just using a like Python level thread pool, and with the byte shuffle implemented using NumPy, like, byte shuffle is really just a transpose operation. We've got about a 6 times speed up so far. I think there's probably pretty easy, there's probably more steps we could do, particularly with the byte shuffle, to speed this up more, but that was already a good first step. And this works for us because we've got like very specific, we know we're using these particular filters, we know about the shape of our chunks, so we don't have to implement a fully general solution, we just have to implement a solution that works for what we're doing. And I think this lends itself to a pretty neat pattern that we can have a check of our expectations. So is this data of a data type that we know about? Does it have the chunking, the kind of chunking we expect, the filters that we expect? Does our access pattern, does the selection match what we know how to deal with? Are we doing any conversion? Are all the data sets similar in these respects? All of this kind of thing. And if it matches this, then we go onto our fast path. And if not, then we can optionally pull back to HDF5. Or we may want to not do that. We may want to just raise an error because, if your program suddenly gets 10 times slower, that's kind of a bug. And it might be a bug that people are not so inclined to report. It might be harder to debug than just an error. So this is what it looks like in extra data at the top on the right. So we have a 4 dataset class method. So this decompressor class will instantiate itself given a dataset, or if it doesn't know how to deal with that dataset, it will say, like, no, can't do this. It will return none instead of an instance. And then once you've got an instance, you call apply filters to actually process the data, to turn a compressed chunk into a decompressed chunk. And this is a very similar conceptual pattern to B2H5Pi, which Francesc was showing yesterday in his talk. So in his case, this opt slice check method checks both the data set and the selection pattern, and raises this no optimized slicing error if it can't handle it, and then it falls back to the this dset.double_get item is H5Pi's like regular read method that will pass through to HDF5. I think there's some improvements to H5Pi that we could do to support this pattern. In particular, B2H5Pi is relying on monkey patching H5Pi to sort of hook in and get in between access. Maybe we should have an API to kind of register these read accelerators. And I think there's also things that we could do about like seeing through virtual data sets, which kind of again gets back to like looking at the format at a lower level. So if you're reading, if you know about the chunking and the filters of the underlying data set, but you're reading it through a virtual data set, you need a way to recognize those underlying data sets, not just the virtual data set that you're looking at. This is all possible because of some nice APIs within HDF5. So the read and write chunk, direct chunk access APIs that various people have mentioned, and then going down another level, these chunk info methods that you can get the offset and the size of the chunk. I'm skipping forwards a bit because I know I'm short on time. I've talked quite a bit about like speeding up reads and writes with these direct chunk access and chunk info methods. I think there's a lot more possibilities that rely on like getting deeper into the file format. and separating the serialization and deserialization of HDF5 from the I/O. That's a tricky thing to do for like the HDF5 format as a whole, because it contains a lot of like, references to other bits. Like, you have to get an offset from this bit of the file and then use that to read another bit of the file. But quite a large part of the format is these object header messages, which probably are tractable for this. And I have been working on this, trying to convert the HDF5, like the human readable format specification, into a machine readable format. There's this language called Kaitai struct. There are probably other languages as well. This was just like the one that I came across. So this is kind of like what it looks like for, this is the version 3 of the chunked data layout description. And you can use all of these definitions to kind of automatically generate parsers in various languages. I have written it for quite a lot of the HDF5 specification, like not that that is enough to read HDF5 files completely, but like, a lot of the details of like just parsing bits of the structure are there. But I haven't extensively tested it yet. I've obviously done little bits of testing. My kind of goal with this is to get it to a point where I can publish these format definitions along with a Python library that makes use of them to kind of get access to the low level, like, these are the object structures within HDF5 rather than trying to recreate a H5Py style API to actually slice data out directly. Oh, I hope I haven't taken too much time and left myself without any time for questions, but thank you very much.
Thanks a lot. I'm sure this is going to trigger a lot of discussion, so yeah, straight away.
Does the parallel decompression run like once per Python requested read to create a big array? Or if you would use Dusk, does it somehow, can you integrate it with your data processing to have like different threads where one thread reads its data and then processes its data only?
Yeah, so yeah, no, definitely the best possibility in terms of parallelizing data access is if we can sort of integrate it more with the processing. And I think particularly actually not so much separating out like, this thread reads and this thread processes, but even like splitting up, okay, we have a batch of threads or processes and like each of them reads and then processes. And then I think you get more benefits of like cache locality and things that way. The challenge for that is that, we're kind of obviously working on this model where scientists are writing code directly and we're providing tools to support them. And a lot of the time, integrating your analysis with parallel processing is more complicated. Like, we do allow for that. You can split the data up and work chunk by chunk, and you can parallelize that way. But a lot of the time, people want to just like load this data in as one thing and then do their analysis. So the thing that I showed about this speed up is just looking at like, can we load an array of data faster, separate from any processing?
Any further questions or comments? If not, then I would actually ask one. So you showed exactly this graph actually. So you've got 10 threads, about 100, so let's say about a bit over 1 second for 1,000 frames. So it's about 100 milliseconds per frame, a little bit below that. How big are the frames?
The frames are, this was Egypt 1M data. So this is
1 megapixel.
1 megapixel. Actually, I can't remember if this was the whole detector or just one module. Yeah, I'd have to look at the details.
Is that the speed you would expect, though? Seems a little slow. And I wonder if you ran into, I mean, we've talked about this before. I think the optimizations on the HDF5 filter plugins package. So if you just take this package from the one from the Nexus formats GitHub repository, and you just download the filter plugins and you just type, cmake and then make and make install, it actually compiles it with -0. So if you just tell it that you actually want it to be optimized, that already makes a huge difference. Like, so from us, it went from 300 milliseconds per frame for 16 megapixel, 16-bit per pixel frame, down to like 40 milliseconds.
Yeah, so we're using in our environment, so this is the filters that we're using are built into HDF5. This is built into HDF5 itself. And we're using the package from CondaForge. So yeah, we're dependent on how CondaForge compiles it.
I imagine they got it right, but
I hope so.
yeah, but it's worth checking.
Yeah.
Good. If there are no further questions, then I think we're. Oh, there's one. Okay, yeah, go ahead.
Have you considered these different ideas for like a sidecar format of HDF5 where you extract the metadata and you have that in some easily readable, and then from that you can directly access the chunks as you need them?
Yeah, so I mentioned here there's this project Ka-Chunk that does this. I wanted to kind of incorporate this more into the talk, but I ran out of both preparation time and talking time. But yeah, that's also an interesting possibility, I think, to like take the chunk information, write a separate index in like a format that's easy for lots of things to read, like JSON, and then you can just like pull out chunks on demand. So Ka-Chunk kind of, you build this separate index, and then you can use ZAR to read chunks out of your HDF5 file without going through HDF5.
Yeah, not to be anti-ZAR, but I mean, we've tried in the past to promote this kind of standardized JSON format for HDF5, but maybe through lack of marketing skill, we've not made much progress in that. But that'd be an interesting thing to examine.
I have missed that there is a standardized format for this, I'm afraid.
Exactly, right.
Okay, there's a very nice looking plate of cakes outside for us. So let's go and eat them. So thank you very much again, Thomas.
Thanks.